All right. I decided to go ahead and create a second video with some more example problems for two-dimensional kinematics. So let's go ahead and take a few more examples and see how do we go about solving these types of problems. So let's start with our first example. Let's say we have a plane. So here's our plane. The plane is traveling with an initial velocity horizontally of 200 meters per second. The plane is currently carrying a package. As it travels along, it's going to eventually drop its package, and of course, the package will go down and hit the ground at some location. The question says this: if the package lands, let's say 2,500 meters from the drop location, that is to say, from when the plane first drops it, this point, to when it hits the ground, that point, the total distance traveled horizontally by this box, by this package, is 2,500 meters. Okay, if that's true, I'd like to find how high up was the plane when it dropped the package. Okay, so there we go. We have a plane. It's some distance up into the air. It's currently flying horizontally with a speed of 200 meters per second. At some point during its flight, it detaches a package that was attached to it, and the package just drops freely, hits the ground. What we know is that from the point it dropped the package to the point the package hits the ground, the package traveled a distance of 2,500 meters horizontally. Okay. And what I'd like to know is what was the initial height of the plane? How high up was the plane when it dropped the package? All right, so how can we go about solving this? Well, let's see, what do we know? First of all, this is a kinematics problem. In fact, these types of problems where an object is either pushed or shot or dropped or something like that, and it just falls by gravity, hits the ground, those are called projectile motion. Okay, projectile motion. So, of course, projectile, you think of a bullet shot from a gun, but anything, if you throw a rock and a rock's free to move under the influence only of gravity, that's a special kind of kinematics problem called a projectile motion problem. Well, so we know there's a projectile motion. We know it's two-dimensional because initially the plane is traveling horizontally, so is the package, of course. And then the package is allowed to drop. So the package is moving left and right and up and down. So it's two-dimensional. And we remember from last time, from the theory of two-dimensional kinematics, that to solve a two-dimensional kinematics problem, we do the same process we did with one-dimensional stuff, except we have to keep track of x directional stuff and y-directional stuff separately. So let's see what we know. The initial velocity. Well, we know this plane had an initial velocity, and we know that initial velocity was purely horizontally, so it was in the x direction. And it had a value of 200. What about the initial velocity in the y direction? Well, the package, of course, is attached to the plane. If the plane is only moving horizontally, the package is only moving horizontally. That means initially, right before it drops the package, there is no initial y velocity. It's not moving up and down yet. So the initial velocity y is just 0. What about accelerations? Well, there's an x acceleration and a y acceleration. What do you know about the x acceleration? Well, remember, the object we're keeping track of here is the package. Okay, the package is the thing we know about. The plane, who knows what the plane does after it drops the package, but the box itself is what I'm talking about. Once the plane has dropped the package and it's now free to fall, is there anything horizontally pushing on the box to try to speed it up or slow it down? Well, of course, in real life, we would say, yeah, there's some wind or air resistance or something. But this is a physics class, first semester. There's no way we're going to go into the real complicated stuff. So we just assume there's no air resistance or wind, unless I tell you specifically there is. So here, once the box is dropped, it's just moving under gravity. Nothing else is pushing on it. That tells me in the x direction, there's no acceleration. However, at the same time, I just said gravity is pulling on it. That's why the box is eventually going to fall and hit the ground. Thus, there must be a y acceleration, and that y acceleration is gravity. And I know gravity is always downwards, so negative, 9.8 meters per second squared. Okay, so I now know the x and y accelerations. What else? What about distances? There must be an x distance and a y distance. The x distance, that is, how far in the x direction will our box travel? Well, I happen to know that. That's given in the problem. The problem says the package lands 2,500 meters from the drop location. That's horizontal distance here. So it's going to travel 2,500 meters. What about y? Do I know the distance that the box is going to travel in the y direction? No, but that's actually the thing I'm looking for. I'm trying to figure out what is this y distance. So that's good. That's something I want to know. So that seems to be everything I know of in this problem. All right, good. What's the next step? Once I've laid out all the information I happen to know and the things I'm looking for, I want to look at my equations. So of course, when you're doing this problem, you're going to have your formula sheet with you. But for me, I'm just going to go ahead and write these formulas down. We know there's x equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is final minus initial velocity over time. And remember, as I said last time, there's an x in this equation. That x means distance. So all three of these equations can mean x stuff or y stuff. Okay, good. Now I can start thinking about my problem. All of this stuff I've done is preliminary setup work, have everything on the page, all the information I need, so that now that I think, how do I go about solving this problem, I could just look and have everything there for me. I don't have to go back to the problem and look into words to find stuff. Let's think. What is it we're looking for? I want to know how high up the package was. That also means I want to know how far the package travels in the y direction. So let's look. Let's say I want to use the first equation. Can I use the first equation to find a distance? Yes, it's got an x in it. Okay. Now, remember, I'm looking for a y distance. So when I look at this equation and say, can I use this equation? I mean, do I have all the y information necessary to solve for the y distance? Well, let's see. I'm looking for y. Do I have the initial velocity in the y direction? Yes, 0. Do I have the time? Ooh, no, I don't have time. Okay, so that tells me I can't use the first equation to find this. All right, what about the second equation? Let's see. Does it have a distance in it? Yeah, there's an x sitting there. All right, I'm looking for a y distance, so do I have everything else about the equation in the y direction? Do I have an acceleration in the y direction? I do. That's gravity. Do I have initial velocity in the y direction? Yes, that's 0. Do I have the final velocity in the y direction? Oh, no. Again, I don't have the information. I don't know how fast this package will be moving when it hits the ground. All right, so let's move on to the third equation. Can I use the third equation to solve for my y distance? No. There is no x in this equation. There's no distance. So here's the first kind of real example where it seems like I don't have the information necessary to solve my problem. The first two equations have distance in them, but the first equation I don't know the time, and the second equation I don't know the final velocity. So I can't use them. If you run into this situation, just remember, you still have the ability to solve the problem. It just might be that you will have to first figure out the piece of information you're missing so that then you could use it to solve the equation for the thing you want. For instance, let's say I wanted to use this first equation. I just figured out I can't use it because I don't know the time. Well, all that really tells me is you don't know the time, but if you had the time, you'd be able to solve it. Can I figure out the time? Well, we say, I can't figure it out in y. That's the problem. But if I use this equation in the x direction, could I use the equation to solve for the time using x information stuff? Well, let's see. I'm looking for t. Do I know the x acceleration? I do. It's 0. Do I know the initial velocity x? I do. It's 200. Do I know the distance in x? I know that. That's 2,500. So I actually have the ability to solve the first equation in the x direction to give me the time. And that's good news, because once I have the time, I go back to the first equation again, only now I do it in y. I now know that missing piece of information. I can solve my problem. So, first step, solve for time. I'm going to look in the x direction to do this. And I say, okay, x equals v naught t plus 1/2 at squared. Plugging my numbers in. X distance is 2,500. X initial velocity, 200 times t plus 1/2. The acceleration in x is 0. And there's my equation to find time. This term goes to 0 because it's multiplying by 0. So t is 2,500 over 200, which is 12.5, I believe. So I now know how long it takes for this package to hit the ground. So that actually, if I were an intelligent question maker, I could have made part A of this question calculate the time it takes for the package to hit the ground. And you'd have to do this to calculate it. But remember, that's not what my question asks. What my question asks is, how far does the package drop? But again, we remember the reason I calculated this time is because I needed it in order to use the first equation to find the distance. So now let's do it. We're looking for y. I'll do it in the y direction. I have the equation x equals v naught t plus 1/2 at squared. All right, I'm looking for distance. V naught in the y direction, 0 times 12.5 plus 1/2. Acceleration, negative 9.8 in the y direction, and t is 12.5 squared. So, what do I get for the distance? I get negative 765.63 meters. Notice I got a negative distance here. That actually makes sense. The package is traveling in the y direction, but it's traveling downwards. So of course the distance should be negative. How far did it drop? 765 meters. And there we go. So you can see this is very similar to what we did in previous examples. The only difference is, in this particular case, in order to solve the problem I'm asked, I first had to solve a different problem that I wasn't asked so that I could use a particular piece of information. In this case, I was looking for the y distance traveled by the package, but none of my equations worked. So that meant I'm missing a piece of information. Let's look to try to find it. In this case, I decided, let me try to find the time, because that would let me solve the first equation for the y distance. The only way I could do it, since I already tried in y and I didn't have the information to do it, I must have to do it in the x direction. I looked, and indeed, I had all the x information I needed to solve the first equation for time. And I plug in my numbers and I get a t. Once done, I now say, okay, now that I have the time, let me solve the problem. Use the first equation in the y direction, plug all my numbers in, and I get my answer. All right, let's try another problem. Something similar. Let's say there is a rock being dropped. The rock is dropped straight down. As it's falling, there happens to be wind pushing on the rock to the left, giving an acceleration of 5 meters per second squared. Okay. If the rock is dropped from a height of 20 meters, I want to calculate the distance away the rock lands. That is to say, I drop my rock, this wind is pushing, so we can imagine the rock is going to be pushed over here and it'll land over here. And what I'm looking for is, what is this kind of displacement? What is this distance here? The rock started falling right here. The wind pushed it as it was falling, and it eventually landed over here. So there's a certain x distance away from the original starting point that this rock will land. And I want to know what that x distance is, given that the rock started with an initial height of 20 meters above the ground. Okay, so there's my question. This is a kinematics problem, studying motion here. There's gravity involved because the rock is going to be falling. It's not purely projectile motion since there is an x acceleration here because of the wind, but it's similar. So we're going to try to attack this problem just like the other ones. Because I have a two-dimensional kinematics problem, let me write down all the information I know in x and in y. So what do I know? Let's say these distances. The x distance, that I don't know, but it is what I'm calculating. The y distance, the rock is going to fall 20 meters, so it's going to travel downwards 20. Accelerations, there's an x acceleration and a y acceleration. The x acceleration is 5 meters per second to the left. Okay, so let's go ahead and calculate it as a negative 5 meters per second squared. The negative just means it's to the left. I could make left positive in my problem, which is probably a better thing to do just so I have less negatives around. But it's completely my choice. There's no right or wrong there. I'm going to use the standard notation of to the left is negative and to the right is positive. So that's why he's negative 5. Nothing about slowing down or speeding up. It's purely the direction. What about the y acceleration? Well, this rock will fall. The reason it's falling is because of gravity. And gravity acts downwards, negative, with 9.8. All right, what else? Velocities. Let's say initial velocity x and initial velocity y. What's the initial velocity of my rock in the x direction? Well, I'm just dropping the rock, so his initial velocity was 0. He wasn't moving before I dropped him. So in the x direction, he's not moving left or right yet, so that's 0. And in the y direction, he also isn't moving yet. So it just so happens the initial velocity of my rock in this problem is 0 both in x and in y. I just dropped it. I didn't throw it or anything. And there we go. That's everything I know from my problem and what it is I'm looking for. I'm looking for this x distance. So, just as before, let's write down our equations. X equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is final minus initial over time. So here we go again. Let's look at our equations, ask the questions. I'm looking for an x distance. Does the first equation have an x, a distance in it? Yeah, x. Okay, do I know everything else about the problem? Let's see, I need to know the initial velocity in x. I know that, that's 0. I need the acceleration in x. I know that. That's 5, negative. Do I know t? All right, I don't know time. So I can't use that. Let's move to the second equation. Does this have a distance in it? It does. There's an x sitting there. Do I know everything about it in the x direction? Acceleration in x, negative 5. Initial velocity in x, 0. Again, I don't know the final velocity in x, though. So he's going to have to be no. I can't use him. Third equation doesn't even have a distance in it, so I can't use that. So here we go again. Here's another example of a problem where none of my 3 equations can be used to calculate what it is I want. So obviously this is telling me you need to calculate something that you don't know yet. What can I calculate? Well, to solve the problem, either I can use the first equation, but I need to know t to do it, Or I could use the second equation, but I need to know final velocity to do it. Which one can I do? Well, let's look at t. Can I calculate t? I already know I can't calculate it in x. Can I calculate it in y? Let's look at the first equation using only y information and see if we can calculate the time. First question, do I know the y distance traveled? Yes, it's negative 20. Do I know the y initial velocity? Yes, that's 0. Do I know, I'm looking for the t, do I know the y acceleration? Yes, negative 9.8. So here we go again. I can use the first equation to calculate t looking in the y direction. So let's do it. Here's my equation, x equals v naught t plus 1/2 at squared. Plugging my numbers in, the y distance is negative 20. Y initial velocity is 0 times t plus 1/2. Y acceleration, negative 9.8 times t squared. So this term is 0 because it's multiplying by 0. And here we go. Can I solve this? I've got negative 20 equals negative 4.9 t squared. I want to get t by itself. So I divide over the negative 4.9. So I have negative 20 over negative 4.9 equals t squared. But again, I don't want t squared, I want t. So square root both of them. T then gives me 2.02 seconds. All right, so what did this tell me? This tells me when I drop the rock, it takes about 2 seconds for it to hit the ground. Good. That's not my answer, so I don't box it, but it is something I need. I calculated this time because I wanted to use the first equation to solve for my x distance, but I didn't know t. Now I know it, so now I can use it. X, that's what I'm looking for here. In order to solve it, I'm going to look in the x direction. Here's my equation. X equals v naught t plus 1/2 at squared. All right, plugging my numbers in. I'm looking for x. X initial velocity, 0 times t plus 1/2. X acceleration, negative 5 times t squared. But I know t, of course, that's 2.02. All right, so this term is 0 because it's multiplied by 0. And so I have 2.02 squared divided by 2 times 5. And I get negative 10.2 meters. So how far will the rock travel horizontally by the time it hits the ground? 10.2 meters to the left. So there we go. Very similar to our first example. We didn't have enough information to solve the problem outright. So I had to solve a different problem first, which was calculate the time it takes for the rock to hit the ground. Once I got that, then I could solve the problem I'm actually looking for. And we see this happens a lot with these types of questions. Because X and Y stuff are different, separate, independent, a lot of times I'll use Y information to solve for something and then use that something to solve for X stuff. But you have to be very, very clear about this. Not one time have I ever plugged X information into a Y equation or Y information into an X equation. The only thing I'm doing is the time. Since the time does not have a direction associated with it, that's why I can take a Y equation to give me something to use in an X equation, because the t itself doesn't have direction. But I couldn't, for instance, use y information to solve for a y distance and then plug that y distance into an x equation. You can't do that. So just be very clear that when I'm doing this, even though I'm using x and y equations and plugging numbers into each other, just take note that the number I'm plugging into the equations here is time. And that's legal since time is not x or y. Alright, so this video is dragging on a little bit, but I do want to get to one more example. Probably the most complicated of these three. But I want to go through it one good time with you so you've seen me solve it. And that way, if you see any other problem similar to this, it will either be like it or easier. So we're going for most complicated here. And here we go. Let's say I have a cliff. And let the cliff initially be 10 meters high. At the top of a cliff is a cannon. The cannon shoots a cannonball with an initial velocity of 40 meters per second. And it shoots it at an angle of 30 degrees. What do we know? Well, of course the cannonball is going to go up and then come back down again and hit the ground somewhere. What would I like to know? Part A, find the maximum height of the ball. And what I mean by that is the maximum height above ground level. Not above the cliff, but above the ground. Okay, so the ball might go 5 meters above where it was shot, but since you're already 10 meters above the ground, you have to add that in to take it into account. What else do I want to know? How about the time of flight? For how long will this ball be in the air? How long will it take to hit the ground? And then, of course, part C is find the range. How far horizontally will this ball travel by the time it hits the ground? Now, we've seen examples like this before. We saw an example where we did a cannonball from ground level, and then it goes up and it comes back down and hits the ground again. But this is different because we're actually starting above the ground. So, of course, that's going to modify things. We also saw a rock shot from a cliff, but usually I either drop it or I fire it completely horizontally. Here, I'm firing it at an angle. So there's a little modification that has to take place here. But what you're going to find is this example is going to be just like the other cannonball example we did, with a slight modification in one or two equations. So, what's the first step? Well, the first step is, first of all, this is a two-dimensional kinematics problem, projectile motion. You're shooting a ball and it's just going by gravity. So I'm going to have x and y stuff. Looking at this problem, there's a big problem. And that problem is right here. My initial velocity is not in x or in y. It's at an angle. And it is imperative that you understand when you're given a piece of information that's at an angle, the very first thing you ever do is break that angle up into x and y components. So, initial velocity, I need an x piece, and initial velocity, I need a y piece. So, let's look. Do we remember how to do this? Here's the velocity, I need an x component and I need a y component given this is 40 and this is a 30-degree angle. Okay. I'm only drawing this to remind you. By now you should be able to do it without having to draw the triangle. But looking at the triangle, if I want the x piece, that x side is adjacent to the angle, and adjacent means cosine. So this is 40 cosine 30. Okay, get your calculator. 40 times the cosine of 30, that's 34.6. The y component, the y side is that side which is opposite to the angle. Opposite means sine, so 40 sine 30, which is 20. All right, good. What else do I know? Well, let's see. Accelerations, x and y. In this problem, once you shot the cannon, I don't see any wind or anything in the problem, so there should be no x acceleration. In the y acceleration, gravity. Gravity is pulling down, so negative 9.8. Distance. I need an x distance and a y distance. Well, how far does the cannonball go in the x direction? I don't know, but that's part C, so that's something I'm looking for. What about the y direction? How far will the cannonball go in the y direction? Now, what I'm about to write is the total distance traveled from beginning to end. So if you notice, the cannon starts here at the top of the cliff, and it lands down here at the bottom of the cliff. Well, just looking in the y direction, obviously the cannon goes from the top down to the bottom, which is a downwards 10 meters. So the y distance traveled here, the total y distance, is going to be negative 10. And in T, I don't know the time of flight, but that's what part B asks for. So there we go. There's all the information I know and what it is I'm looking for. So let's start. Part A, max height. Well, by now, I've done a bunch of cannonball problems. Hopefully you've done a bunch of cannonball problems. And it's clear, every time we want to find maximum height, that tells me two things. Number one, I'm looking for a distance in the y direction. So whatever equation I'm about to use, better have distance, and it better only use y-directional information. And it turns out, every single time, we always use this equation, the second one. Vf squared is v naught squared plus 2ax. And we use it in y. Why do I use this one? Well, I'm looking for a distance. There's the x, distance. I need an acceleration in y. I've got it. I need an initial velocity in y. I calculated it. And I need a final velocity in y. Well, I don't have that written, but if you remember in the argument I gave last time when we talked about the cannon, we said this particular part, I'm looking for maximum height, which means I'm at the very top of my motion. So if that's true, if I'm at the very top of my motion, then how fast must I be traveling in the y direction? Well, I better be traveling at 0. I better not be moving at all. Because if I'm still moving up, then I'm not yet at the top. But I'm saying I'm trying to find it when I'm at the top, so I better be at the top. So the only way I can be at the top is if I've stopped moving in the y direction. Thus, the final velocity in the y direction at the maximum height is always 0. Once I have that, then this is easy. This is 0 equals initial velocity y is 20 squared plus 2. Acceleration in y, negative 9.8. times my y distance. Now notice, this is a y distance, and over here with my information stuff, I have a y distance already plugged in, -10. But that's a different y distance. That's a total distance for the whole flight. But this part A, I'm looking for something different. It's still a y distance, but it's only partial distance. It's only once you get to this point up here, this distance. Call it h or something. That's the distance I'm looking at in part A. So I can't use the y for my data for the problem because that's the total distance y, not just the maximum height. But anyway, here we go. There's my equation. I've got all my numbers plugged in. So just rearrange things to solve for y. Bring the 20 squared over, so -400 equals 2 times -9.6 is -19.6 times y. I want to get y by itself, so divide it over. I get y equals 400 over 19.6, which 400 over 19.6 is 20.4. Okay, I'm tempted to box this answer. Ask yourself, is this the right answer? Is this the maximum height? Well, what do you think? No, it's not. Remember, I was very explicit in part A here to say I want the maximum height above the ground. What did I just calculate? I drew it on my picture. I drew the maximum height above where I started from. So I started from the top of the cliff, and then I went an extra 20 up. But what I'm looking for is the total height from the very bottom ground. So the real height then is, call it y max or maximum height, however you want to label it, it's up to you, is my 20.4 plus the initial height of my cliff, the extra 10 meters. So the real maximum height is 30.4 meters. All right. So there we go. Part A done. Found the maximum height. How did I do it? I'm looking for a y distance. Also, I know, because it's always like this, if I'm at the maximum height, my y velocity is always 0, my y final velocity. So I use the second equation, vf squared is v naught squared plus 2ax. Looking for the distance. Acceleration is gravity. Initial velocity, I happen to know. Final velocity is 0 at the maximum height. Plug my numbers in. I saw for my y, I got 20.4. That 20.4 means from where I was originally shot, I went an extra 20.4 meters up. The question said the maximum height above the ground. So it's 20.4 plus the height of the cliff, which was 10. So 30.4. Okay. Now, I'm going to have to go to another page, but I'll go ahead and redraw the picture here. Here's my cliff. The ball, shot, up and back down again. 10-meter high cliff, 30 degrees, and initial velocity of 40. All right. Now I'm looking for part B. Part B was time of flight. So the total time that the ball is going to be in the air. All right, let's look at our equations. We have x equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is final minus initial over time. Okay. I'm looking for time. First equation has time in it. Okay, I have two choices. Either I look in the x direction or I look in the y direction. Can I look in the x direction? Well, in order to do it, I need to know the acceleration in x, which I know is 0. I need to know the initial velocity in x, which I calculated. And then I need to know the distance the ball moves in the x direction. That I didn't know. So I don't have the information required to solve the first equation in x for time. So let's look in y. Can I do it in y? All right, looking for time. Do I know the y acceleration? Yes, it's gravity. Do I know the y initial velocity? I do. That was 20. I just used it, in fact. Do I know the y distance traveled for the ball? I actually know two y distances here. I know the total distance, which was from the top of the cliff all the way back down to the bottom, which is negative 10 meters. And I know the maximum height. Which of those two do I use to find the total time of flight? Well, it seems evident to me that if I want the total time, I better use the total distance. That is, where were you before you were shot? Where did you wind up after your shot? That's the total distance. And of course, looking at my picture, I started here. At the end of the day, I landed here. What's this y distance? Well, that's my little green 10, the height of the cliff. It doesn't matter how high up it went or anything like that beforehand. All you care about is final and initial. The final location, down at the ground. Initial location, top of the cliff. What's the difference? Negative 10 meters, because you went downwards. So I know the y distance. All right, I can use, looking in the y direction, I could use the equation x equals v naught t plus 1/2 at squared. And I'm going to use this in the y direction to solve for t. All right, let's plug our numbers in. What's the y distance traveled? Negative 10. I started at the top of the cliff. Stuff happens. I don't care about the stuff. I'm now down at the bottom of the cliff. How did I change? I went downwards 10, so the y distance is negative 10. Equals y initial velocity. Let's see, I had this over here. Y initial velocity was 20 times t, which is what I want, plus 1/2 negative 9.8 t squared. Okay, again, be very careful. This initial velocity is not the total initial velocity of 40. It's not the x initial velocity, it's the y initial velocity. Because all the information in this problem is all in y. All right, so there's our equation. Unfortunately, it doesn't look so nice. This is looking like it's about to be quadratic. But let's clean it up. Let's get everything on one side. So I'm going to move everything to the right. I have 0 equals. I'm going to write the t squared term first. 1/2 of negative 9.8 is minus 4.9 t squared. Then I have the 20t. Then I bring the negative 10 to the right side. That becomes positive 10. And there's my equation. This is now quadratic equation in standard form. How do I know that? Well, we have a t squared b times t plus c. So a is this whole number, negative 4.9. B is 20. And c is 10. And now all I have to do is use my quadratic formula, which says t will be equal to minus b plus or minus square root of b squared minus 4 times a times c, all divided by 2a. Now I plug those numbers in. Minus b, so minus 20, plus or minus square root of b squared, 20 squared, minus 4 times a. A is negative 4.9 times c. C is 10. All of that is divided by 2 times a, which is 2 times negative 4.9, which is negative 9.8. All right, well, still kind of messy, so let's try to simplify. Negative 20 plus or minus square root. 20 squared, that's 400. The rest of this, I've got 4 times 4.9 times 10, which is 196. And then is it positive or negative? Well, it's minus times minus, which is positive. And then all of that is divided by 9.8. All right. So, negative 20 plus or minus square root of 400 plus 196 is 596. So this is going to give me 2 answers because of the plus or minus. Let's look at the plus first. The plus says negative 20 plus the square root of 196. And what's the square root of 196? I mean 596, I'm sorry. The square root of 596 is 24.4 divided by negative 9.8. And what is this? So that number minus 20 over negative 9.8. This gives me an answer of negative 0.45. Okay, so there's one answer. What's the other answer? The other answer, let's use the negative. So it's going to be negative 20 minus 24.4 over negative 9.8. All right, so negative 20 minus 24.4 divided by negative 9.8. And this answer gives me positive 4.53. All right, so unfortunately tedious. We had to use quadratic formula here. We're looking in the y direction, just going over this part again. Looking in the y direction to calculate time. Plugged all my numbers in. Found out I have a quadratic equation, so I need an A, I need a B, and I need a C. Remember to include negatives and positives. So for instance, A is not 4.9, it's negative 4.9 because of the negative. I then use quadratic equation. Then just replace the A, B's, and C's with the numbers. Then you just take step by step, simplifying the numbers down. Eventually you get down to this right here, which has a plus or a minus in it, which means 2 different answers. One answer you use the plus, the other answer you use the negative. The plus answer gave me negative 0.45 as an answer. The minus gave me 4.53 as an answer. Now obviously, I can't have 2 answers here. Why can I not have 2 answers? What do you think? Well, the reason I say we can't have 2 answers is we're looking for the time it takes for the ball to hit the ground, the total time of flight. Well, if I shot a cannon, the ball's not going to land at 2 different times. It's going to land 1 time. So only one of these times must be true. Which one is the right answer? Well, we all have intuition. Could it be negative 0.45? Well, that would mean the ball hits the ground 0.45 seconds before I shoot it. Obviously, that doesn't make sense. The ball has to land after I shoot it. So I better have a positive answer. Thus, I must be using 4.53 as my answer for the time of flight. The negative answer is immaterial. We don't need it. A mathematician would say you have to include it as an answer because it's a legitimate answer. But I'm not a mathematician, I'm a physicist. And a physicist says, while there may be certain true, real answers mathematically, all I care about are the physical answers. And there's only one physical answer for how long it takes for the ball to hit, and it's the positive time. So that's part B. One more part to go, but thankfully it's kind of small, so I could fit it down here. This one's not so bad. What was part C? Part C says find the range. That is to say, how far horizontally will this ball travel? So that is from here, from the starting point to the ending point, find that distance. All right. Well, that tells me two things. Number one, I'm looking for a distance. Number two, I'm looking for it in the x direction. So, I'm looking for a distance. Which equation will I use? Can I use the first equation? Does it have distance in it? Yes. I'm looking in the x direction now. Do I have everything I need in the x direction to solve for the x distance? Well, I'm looking for x. Do I have the initial velocity in the x direction? Let's check. V naught x is 34.6. Yes, we have it. Do I know the time that it takes for the ball to get to the final location? Yes, that's what I just calculated in part B, 4.53. Do I know the x acceleration? Let's look back. I do. It's 0. Of course it's 0. There's nothing pushing on the ball. There's no wind or anything. So the x acceleration better be 0. So good. I have all the information I need looking in the x direction and using the first equation. X equals v naught t plus 1/2 at squared. I'm looking for x. V naught x, what was it again? 34.6. Don't be tempted to put that 20 in here. The 20 was the y initial velocity. This is the x. Time of flight, 4.53 plus 1/2. X acceleration is 0. 4.53 squared. This term is 0 because it's multiplying by 0. And so I have 4.53 times 34.6, which gives me 156.8 meters. And there we go. So, looking back at this question, if you notice, it's almost identical to the cannonball question we had last time. That was shot at level ground. We had to calculate the maximum height. In order to do it, we look at the second equation in the y direction, given final velocity in the y direction at the maximum height is 0, and we solve for the y distance. It differed from that example because we had to add in the fact that we were already 10 meters above the ground. But that's okay. We're intuitive. We can figure that out. You just have to be careful not to rush through the problem and forget it. All right, what about part B? Part B, time of flight. Just like the other example, we are using the y directional information to calculate how long the ball will be in the air. But in the other example for the cannonball, we had the luxury of having the y distance be 0, because when the cannonball was shot from level ground, it started on the ground and it ended on the ground. So the total change in the y distance was 0. So that made this number right here, this -10 here, be a 0. And once that was a 0, we didn't have a quadratic equation anymore. So for the other example, it was easy to get the answer for time. Unfortunately, with this one, it wasn't 0, because we're starting at the top of the cliff and we're ending at the bottom of the cliff, which means there is a difference in the y direction, or distance. In this case, it drops 10 meters, so -10. All that meant was still using the same equation, plugging the numbers in just like usual, but now the algebra was different. I had to use a quadratic formula to get my time. The quadratic formula, of course, implies I have two answers, but only one of them is realistic, one is physical. And in general, you're going to find that one of the times is negative and one of the times is positive. Not always, but usually it's like that. If it's like that, you always take the positive one. If it's not like that, if they both happen to be positive, then you just use your intuition and you think which of the two times makes sense. Because you might get something like 3.2 seconds and 450 seconds. Well, obviously, the answer is probably not 450 seconds. Okay? But in general, it'll be like this. One's negative, one's positive. You know it's not the negative answer for time, so you take the positive one. And in part C was identical to the other one. You're looking for the x distance traveled. The x acceleration is always 0. So you plug in your x information and you get your distance. I promise, on an exam, you will not have a kinematics problem harder than this one. It could be different. I could have something like this. You shoot a golf ball up to a raised green, and it lands up here, where you have an initial velocity of 40 at an angle of 30 degrees, and maybe the green starts 2 meters above your location and asks the same questions. What's the maximum height? What's the time of flight? And then how far away is the green? That's the range. And you're going to do it identical to this problem. The only difference is going to be when you're calculating the time and you're looking at what y distance will this ball travel. For this example, it travels downwards -10, of course. But for this example, it's going to travel upwards. So that y distance would be a +2. But other than that, you still go through this quadratic formula thing with those numbers. So, this is something you have to be used to. If you get on a test or a homework problem and you say, oh my God, I never got this example before. He never did this example for us. How am I supposed to be able to do it? Don't think that way. I'm telling you, I'm never going to give you a problem that I think is unfair to you because you have no idea how to solve it. You should be able to solve this particular golf problem right now, given what we just did, because it's identical. The only thing, forgetting about the picture, forgetting about everything else, there's only one difference. And that difference is, for the one we just did, the ball travels down 10 meters in the y direction. In this example, the ball travels up 2 meters instead. Other than that, this is identical in every way. So, you have to be able to recognize that when you get a question you haven't seen. Don't say, oh my God, I haven't seen this. There's no way I can do it. Rather say, I haven't seen it, but it reminds me a lot of this other one I did do. Can I use that method to solve this problem? And I promise you, you will be able to. So anyway, I hope these examples have been helpful for your homework and also just for practicing. You need to practice those problems that are posted. Practice any problems we've been doing. Go back over them after you've done them on a blank sheet of paper and try to do it again without looking at your notes or anything. When it comes time for a test, you should be able to take any of these examples or the previous ones we did in class and have a blank sheet of paper in front of you and only your formula sheet and be able to think your way and reproduce it. You should not have to use your notes to get through these questions. Right now, it's perfectly fine if you have to use your notes and you have to watch these videos and do it along with me. That's why we're doing this now. But for test time, you want to be so comfortable that you can close your notebook and still be able to do this stuff. That's the point you need to get to. So keep practicing even after you're sick of it and you're tired of it. I know this is the most entertaining, brilliant, exciting stuff you've ever done, but even so, I'm sure you're going to get sick of it. And that's a good sign. It means you've practiced it a lot. Once you're sick of it, it means I know this so well, it's boring to me. There's nothing new to it. If you get to that point, then you could be here recording these videos for other people. So get to that point, especially before this test, because I'm telling you, nothing will make me happier than when I sit down to have to grade everyone's exams, all of these answers are 100%, and I just have a nice, fun evening putting check marks and hundreds on exams. I'd love that. So I'm not going to purposely give you difficult, challenging problems to trick you. But I will give you legitimate problems, expecting that you've gone through these practice problems yourself. Because I have to be fair. Anyway, as I said, hope these have been helpful. As always, if you're having questions, if you're having trouble figuring something out or why I used a number the way I did or whatever, email me and I could talk you through it. We could exchange pictures of the work or even do a Zoom meeting or meet in some way if that's helpful too. That's what I'm here for. Until next time.